Dear students, so far you have studied up to partition of a set. What is partition of a set? Partition of a set. And I explained one important theorem. What was that theorem? An equivalence relation in a non-empty set becomes partition of a set, and converse also. A partition of a set defines an equivalence relation. That was the important theorem. And also I have considered some examples. Now, first I start with two definitions and then indexed family of sets and generalized De Morgan's laws. I try to cover these things in this video. First is definition of quotient set, partial order relation, what are indexed family of sets, then the generalized De Morgan's laws. I try to cover these things. First of all, what is quotient set? So the definition is like this. Definition of quotient set. Suppose S be non-empty set and R be an equivalence relation. R be an equivalence relation on S. Then this R defines equivalence classes. Equivalence classes on S. Equivalence classes on S. And these equivalence classes partition S. These equivalence classes becomes partition of S. And that set of all equivalence classes which partitions the non-empty set S is called quotient set of S, determined by R. Determined by R and is denoted by this notation S by R or simply S dash. That is the definition of quotient set. Let me explain once again. Suppose S is a non-empty set, any non-empty set, R be an equivalence relation defined on S, then this equivalence relation defines some equivalence classes in S. That equivalence classes defines a partition of S. It defines a partition of S. And the set of all that equivalence classes which partition S, which becomes a partition of S, is called the quotient set of S, determined by R and is denoted by S by R or S dash. This is the definition. So definition is like this. Let S be a non-empty set. S be a non-empty set. Let capital R be an equivalence relation. You know what is equivalence relation? Reflexive, symmetric and transitive. It is called equivalence relation defined on S. Defined on S. The set of all mutually disjoint equivalence classes in which S is partition is called a quotient set of quotient set of S determined by R. Determined by R. It is denoted by S by R or S bar. Example, consider set of all non-zero integers. Set of integers is denoted by I. Now consider equivalence relation congruent modulo 5. Congruent modulo 5 is an equivalence relation. In I. This example we have already discussed. What is that? Congruent modulo 5 is an equivalence relation in I. Now what are the equivalence classes determined by this equivalence relation? They are 0, 0, 1, 2, 3, 4. This 0 means it is not only integer 0, it is a equivalence class. It determines the set which are congruent to 0 mod 5. 1 means integers which are congruent to 1 mod 5. What is this one? 0 means, this we have already discussed, but let me explain once again. What is this set 0? Here 0 is a set, not a single integer. What is this 0? 0 is 0, 5, 10, so on, minus 5, minus 10, and so on. It is infinite set which are congruent to 0 mod 5. 1 means, what is 1? Integers which are congruent to 1 mod 5. 1, 6, 11, so on, minus 4, minus 9, etc. They are congruent to, all are congruent to 1 mod 5. Take 6. 6 is congruent to 1 mod 5. 11 is also congruent to 1 mod 5. All these are, it is called a set 1. It is the equivalence class determined by 1. Now, this set is called quotient set of I determined by R. Quotient set of I determined by R. What is that? That set is 0, 1, 2, 3, 4. This is the definition of quotient set. Next definition is partial order relation. Partial order relation. We have studied equivalence relation. What is equivalence relation? Equivalence relation means a relation R in a non-empty set S is called equivalence. It is reflexive, symmetric, and transitive. Now, partial order relation, it is defined like this. A relation on a, suppose S be a non-empty set. A non-empty set. A relation capital R on S is called a partial order relation. Partial order relation if R is, first one, reflexive, second, antisymmetric, third one, transitive. Then this R is called partial order relation. Here you know what is reflexive relation. What do you mean by reflexive relation? For all x belongs to S, I have taken S as the non-empty set. Yes, the order pair XX belongs to R. Then we say that it is reflexive. Second, for all XY belongs to R, YX also belongs to antisymmetric. XY belongs to R, YX belongs to R implies X is equal to Y. What is symmetric relation? Symmetric means For all xy belongs to R, yx must belongs to R. But anti-symmetric means for all xy belongs to R, yx belongs to R implies x is equal to y. Then the relation is called anti-symmetric. I give an example for partial order relation, it will be clear. This is the definition of anti-symmetric relation. For all xy belongs to R, yx belongs to R implies x is equal to y. And it must be also transitive. What do you mean by transitive? Transitive means xy belongs to R, yz belongs to R implies xz belongs to R. Then it is called transitive. So if the relation is reflexive, antisymmetric and also transitive, then it is called partial order relation. Now I give example for this partial order relation. Example for this is in the set of natural numbers n, the relation defined by A divides B is it is partial order relation because it is reflexive. Why it is reflexive? Example is non-empty set is set of naturals. What is the relation here? It is defined by this A divides B. Then it is reflexive because A divides A always. A divides A is true. Therefore it is reflexive. It is antisymmetric because if A divides B, B divides A, then this implies A is equal to B. If A divides B, B divides A, it implies A is equal to B. So it is antisymmetric. Why it is transitive? Because divisibility is transitive. It is transitive. Let A divides B, B divides C. This implies A divides C always. So this relation is partial order relation. Important: reflexive, antisymmetric and transitive. Then it is called partial order relation. Partial order relation. So we have studied, I think you all of you followed two definitions. What is quotient set? What is partial order relation? Next is indexed family of sets. Indexed family of sets. I explain what are indexed family of sets. Family of sets indexed by some non-empty set. See, the definition is like this. Let capital lambda be any set. Then a collections of sets such that to each lambda belongs to lambda. So this is the lower case and this is the upper case. These are the Greek letters. This capital, it is upper case, capital lambda. This is small lambda. Suppose for each lambda belongs to lambda, there corresponds a member of the collection. Then it is called indexed family of sets. Here this lambda is called index set. And the indexed family of sets is indexed by lambda. It is index set. And it is denoted by A is set of all A lambda such that lambda belongs to lambda. This is the notation for indexed family of sets. A is it is indexed family of sets indexed by lambda, and notation is A is set of all A lambda such that lambda belongs to lambda. If I give example, it will be clear. Example is like this. Let A is equal to, first example, set of all an such that n belongs to n, and an is, it is defined like this. An is set of all x such that x belongs to n and x is a multiple of n. A multiple of n. See, first example is, suppose A is set of all an, n belongs to n. A is indexed family of sets. It is an, defined as an. What is an? Set of all x. X belongs to n. X is multiple of n. Then what is a1? A1 is multiple of 1. 1, 2, 3, 4, so on. What is a2? A2 means, what is A2? Set of all x. X is a multiple of 2. So 2, 4, 6 and so on. A3, it is 3, 6, 9 and so on. An is, it is n, 2n, 3n and so on. So what is A? A is set of all this. A1, A2, A3, etc. An. It is n is index set here. So this is the definition of indexed family of sets. See, in this example, A consists of these sets: A1, A2, A3, An. What is A1? A1 means again a set it is. Family, therefore A is indexed family of sets indexed by this n. What is A1? 1, 2, 3, 4, etc. A2, 2, 4, 6, etc. A3, 3, 9, 6, so on. Indexed family of sets. Next, second example for indexed family of sets. This is quite a new concept for you. You have not studied in earlier classes. What is indexed family of sets? Therefore, to make the this definition more clear, I take one more example. Let capital N be natural numbers, set of all natural numbers. Let An be the set of all natural numbers, set of all rational numbers with denominator n. Then, see, the definition is like this. N be the set of all natural numbers. What is An? An be the set of all rational numbers with denominator n. Then A is set of all An such that n belongs to n. An set of all rational numbers with the denominator n. An is set of all n belongs to n. What is A1? How it is defined? Now An is defined like this. A1 is all the rational numbers with denominator 1. What are the rational numbers denominator 1? Plus or minus 2, plus or minus 3, so on. These are the rational numbers with denominator 1. A2 is rational numbers with denominator 2. What are that? 0, plus or minus 1 by 2, plus or minus 2 by 2, plus or minus 3 by 3, so on. A3 is 0, plus or minus 1 by 3, plus or minus 2 by 3, plus or minus 3 by 3, so on. Here, How the indexed family of sets is defined? It is set of all an, and how an is defined? An is defined like this: set of all rational numbers with denominator n. So a1 is this, a2, a3, and so on. Now the union and intersection of these indexed family of sets is important. Definition will be clear. We go through the notes which is provided for you. Hard copy of the notes will be supplied for you. Go through that one. And if you have any difficulties, you can ask it anytime. In the next video, I consider union and intersection of indexed family of sets and generalized De Morgan's laws. Always on generalized De Morgan's laws, there will be one question in the examination. I consider that in the next period. Next period means in the next video. Yes, thank you.